last left off at epsilon naught. So we did one example, we went past that, we did epsilon naught plus 1. And like before, we can keep on going like this, epsilon naught plus 2, epsilon naught plus 3. We can even do epsilon naught plus omega, epsilon naught times omega. Eventually what we want to do is we want to get up to the next time where this equation is true. So the next fixed point of the epsilon map, so to speak. So we're going to do a little trick basically. Like I showed you before, omega of epsilon naught is just going to equal epsilon naught. But if we take omega epsilon naught plus 1, we actually get a bigger ordinal. And we can see this just by doing a little bit of math here. So we use rule of exponents and we turn this into omega epsilon naught times omega. This is going to turn into epsilon naught. And we just get epsilon naught times omega, which is a bigger ordinal. So we're going to use this kind of trick here to create another tower, infinite tower of omegas, and then just plop this thing on top. So you can imagine, like, if we want to make bigger and bigger ordinals, we can do like omega to the epsilon naught plus 1, omega to the omega to the omega of epsilon naught plus 1, blah, 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 blah. And we can keep on going and going and going and going and going until we finally get omega to the omega to the omega to the omega, infinite number of omegas, and we just plop epsilon naught plus 1 on the top of it. Now this satisfies this equation here. WA is equal to A. So we're going to call this the second fixed point of the epsilon map. And as such, we're going to give it a name. So if the last one was epsilon naught, we're going to call this one epsilon 1. So that equals this blah, 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 blah. That's 1. And this kind of keeps on going like this. Epsilon 2 would be denoted as omega, 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 epsilon 1 plus 1, etc., etc., etc. So the epsilon number, you're going to get the tower of omegas with the previous epsilon number plus 1 at the very top. I'm going to do one example of these because it might not be so clear if we plug one of these into the fast-running hierarchy, how we would evaluate that. So let's do an example of epsilon 1. We have f of epsilon 1 of 3. How would we evaluate that? Well, the same kind of idea, how we diagonalized epsilon naught in, as it was the number of omegas in the tower, it's the same kind of idea. It's a little bit different, like, just to make things confusing. The number of omegas in this tower actually is this number. Like with epsilon naught, if you remember, it was this minus 1. So f of epsilon naught of 3 was omega to the omega. But this actually is, you take this number and that's the number of omegas. And again, there's a reason for this and we have to use Veblen functions to figure that out. So that's going to come a little bit later. I'll show you why this is the case. But so for epsilon 1, basically we take this number, we draw that many omegas, and then we plop epsilon naught plus 1 at the top. And that's of 3. And then we can use rules of exponents, like we can take omega epsilon naught plus 1 is equal to omega epsilon naught times omega. So we get this collapses down to epsilon naught. That's a 3. We get f omega to the omega epsilon naught times omega. This gets diagonalized, so you have 3 copies of this. You could keep 2 copies of this and get another epsilon naught, which would diagonalize to omega to the omega. So basically you're doing rules of exponents and whatnot, same things that you would have learned in high school. It's all the same math from here on out. It's just a little bit tedious when you get to the higher numbers, but it's all stuff that you can do yourself, type of thing. Okay, so we can keep on going up through the epsilon numbers arbitrarily until we get to epsilon to the epsilon to the omega. And this is totally okay. We're allowed to do this too. We can diagonalize this if we plug this into the fast-growing hierarchy. This just goes in this slot, so we can diagonalize this, and this turns into F epsilon 3 of 3, and that's something that we can evaluate. This would turn into a tower of omegas that's 3 high, plug in epsilon 2 plus 1 at the top, blah, blah, blah. That's something that we're able to evaluate. And we can keep on going. We can even do stuff like epsilon omega plus 1, epsilon omega plus 2, epsilon omega times 2, epsilon omega to the omega. We can keep on going like this. We can do all the ordinals that we did before and plug this into the subscript of the epsilon. And we can even do epsilon with a tower of infinite omegas, which is epsilon naught. So we have an epsilon in the subscript of an epsilon. So if we were to diagonalize this in the fast-growing hierarchy, very simply, we use the same thing as we did before with the epsilon naught. This would just be epsilon of omega to the omega, and that omega would turn into a 3. So we'd have something like epsilon to the omega cubed. So that's totally okay. We can do that. And it goes further. We can do epsilon of epsilon of epsilon naught, epsilon of epsilon of epsilon of epsilon naught, and do these nestings of epsilon functions. But wait a minute, we're going to reach another limit pretty soon. What about an infinite cascading of nested epsilon functions? Well, this, as it turns out, is another infinite ordinal. And this is the infinite ordinal that satisfies the equation EA is equal to A. So if you imagine this is an infinite nesting, if I put another epsilon in here, this is going to stay the same. So this satisfies this equation. And this ordinal is often called Zeta naught. And again, we can use this in the fast-growing hierarchy. So I'm just going to erase this, get a new page. Let's plug in Zeta naught. Okay. F of Zeta naught. So the same kind of idea, except this time, to figure this out, this number here is going to be the number of nested epsilons. So you're going to have F epsilon of epsilon. I can't actually remember if it's, I'm pretty sure it's the actual number. So you're going to have 3, and then you're going to have Zeta naught plus 1. So the same kind of idea of how the epsilons were a tower of omegas with omega 1, or epsilon naught plus 1 at the top. This is a nesting of epsilons with Zeta naught plus 1. So there's always this kind of a plus 1 thing to get you out of the trap of having something like epsilon Zeta naught just turning into Zeta naught, kind of collapsing on itself. So you keep this here so it expands into something bigger and doesn't just collapse on itself. And because you understand how this works, like this is just a infinite cascading of epsilon, so this is just the same if you plot one up here. So that's why this equals that. Now you can kind of see where this trend is going. We can do the same thing here, so we can go Zeta 1 is equal to an infinite nesting of epsilons with Zeta naught plus 1 at the very bottom. We can do Zeta 2, Zeta 3, we can do Zeta omega, we can do Zeta epsilon naught, and then eventually we get to things like Zeta of Zeta naught, and then Zeta, oh, I can't even draw these things, so many. We can do this often to infinity. And that's going to be another thing, another one that satisfies the equation Zeta of A is equal to A. But this can keep on going forever, and there isn't an infinite number of Greek letters in the alphabet. So it seems like we need a more robust mathematics to deal with all of these new functions we're going to get that are going to keep on going off into infinity, like infinite nestings of these new infinite ordinals. So this is going to be Veblen functions, which I alluded to earlier. That's going to allow me to show you why certain things are true, like why diagonalization of epsilon naught turns out to be a tower of omegas that's n minus 1 and stuff like that. So that's going to be in the next video.